Hi guys, you're welcome to my channel. Today we are going to be talking about wave. And what is wave? A wave is a disturbance that travels through a medium and transferred energy from one point to another. The transfer of energy from one point to another without the permanent displacement of the medium. So a wave usually comes in form of an oscillatory or vibratory motion, and it transmits energy from one point to another through a medium without causing a permanent displacement of that medium. When we talk about wave, we have types of wave to include water wave. This is an example of wave. We have sound wave and we have light wave. So when you talk about water wave, the material medium to transfer energy from one point to another is water. So when you talk about water wave, the material medium there is water. Then when you talk about sound wave, the material medium for sound wave is air. Are we there now? And when we talk about light, you can pause the video and tell us what will be the material medium for transferring light energy from one point to another. Because we understand that water wave uses water to transfer energy from one point to another, and at the same time we understand that for sound energy to transfer, there must be presence of air. In other words, in vacuum where there is absence of air, we cannot transfer what? Sound. Are we together now? So, air is the material medium for sound wave. Now, what is the material medium for transferring energy from one point to another? This is quite technical. Some scientists say the material medium for transferring light energy from one point to another is called ether. But these characteristics of ether made us understand that ether does not exist. A scientist called Orin is the one that proposed what? That ether is the material medium for transferring light energy. Now, what makes us believe that ether does not exist? He said ether has zero momentum. And for a body to exist, if that body is moving, because something that will transfer energy from one point to another must also be in motion. Hence, that body must have velocity. Any body that exists, no matter how small it is, it must have what? Mass. The product of mass and velocity is what we refer to as momentum. Product of mass and velocity is called momentum. So if momentum of a body equals zero and the body is moving, that is, the body has a velocity, it means the body does not have mass. When a body does not have mass, it shows that it doesn't exist. Hence, we conclude that light wave does not have what? Medium. Now, if light wave has no medium to transfer energy, and it's transferred energy from one point to another, while we have water wave, sound wave that transferred energy with medium, then we can categorize wave into two. Those that has to do with material medium and those that has to do with no material medium. So we can then say classes of wave. So when you talk about the classes of wave, we have one, the mechanical wave, and we have two, the electromagnetic wave. Now, when you talk about mechanical wave, they are waves that require material medium for their propagation. That is, they cannot transfer energy from one point to another without a material medium. Example of mechanical wave includes the water wave, the sound wave. These are examples of mechanical wave. This wave required material medium. But when we talk about electromagnetic wave, they are waves that doesn't require material medium for their propagation. That is, they are not in need of material medium to transfer energy from one point to another. An example of such wave includes light wave and electromagnetic radiation. Electromagnetic radiations. Do we understand this now? So when they say classes of wave, you can classify wave into two: mechanical and electromagnetic. Example of mechanical wave includes water wave and sound wave. Example of electromagnetic wave includes light wave and electromagnetic radiations. Do we understand this now? Now, for us to understand what we call electromagnetic radiations better, there is need for us to look at electromagnetic spectrum. When you talk about electromagnetic spectrum, of which I will be making video to explain it in detail with time. But for now, for us to just understand the category of electromagnetic radiation, when you talk about electromagnetic spectrum, they are the arrangement of electromagnetic radiations in order of increase in wavelength and decrease in frequency, or vice versa. So when you arrange electromagnetic radiations in order of their increase in wavelength but decrease in frequency, or you arrange it in order of decrease in wavelength, increase in frequency, we call it electromagnetic spectrum. So in the spectrum, we have redox G. When you talk about redox G, R represents radio wave, I represents infrared, V represents visible light, and U represents ultraviolet, X represents X-ray, and G represents gamma ray. So this is radio wave, radio wave. This is infrared radiation. Here is visible light. Here is ultraviolet, here is X-ray, and here is what? Gamma ray. Now, the way they highlight this, that is the redox G. Let me write it here. Redox G. As they highlight this, this is the order of their increase in frequency. That is, as they move from radio wave down to gamma ray, their frequency is increasing. That's to tell you that the frequency of gamma ray is greater than the frequency of radio wave. In other words, the frequency of radio wave is the shortest frequency out of the spectrum. Are we together now? Why gamma ray has the highest frequency? This order of increase in frequency but decrease in wavelength, are we there? This order of increase in frequency is also known as the order of decrease in wavelength. The order of decrease in wavelength is the same thing as the order of increase in frequency. To tell you that radio wave has the highest wavelength but the shortest frequency. Gamma ray has the highest frequency but the shortest wavelength. But one thing is constant for all these radiations. And what is that thing? The thing is that they all move with the same velocity. They all move with the same velocity. And their velocity is what? The speed of light. The speed of light. So when you talk about the speed of light, we are talking about 3 times 10 raised to power 8 meter per second. This is very great speed. That is 300 million meter in 1 second. When you say 3 times 10 raised to power 8 meter per second, it shows that light can cover a distance of 300 million meter in 1 second. And we consider this to be the limiting speed. That is the highest speed ever. Are we together now? Good. If that should be the case, we can now what? Move on to consider some other things about wave. Okay, so we can now talk about the description of a wave. How to describe a wave, or we call it the terms used in wave. When you talk about the terms used in wave, that is the terms that we use to describe wave, we have one, crest. Okay, let me start from wave profile. We have wave profile, we have crest, we have trough, we have amplitude, we have wavelength, we have frequency, we have period. Here are some terms that we use in describing wave. Now let's take each one after the other for better explanation. When you talk about wave profile is the diagrammatical representation of a wave. When you use a diagram to represent a wave, that diagram is called wave profile. Example include this. So this is a wave profile. The wave profile can be displacement in meter against time. Are we together now? Displacement in meter against time. And you can also plot the displacement against its position. Are we together now? That is y against x. So, but in most cases, we plot displacement against time. So, this is representing wave. And this diagram is called a wave profile. Now see, the next one is called crest. The displacement upward of a wave is what we refer to as crest. When a wave displaced in upward direction is known as crest. Then the next one is trough. The downward displacement of a wave is what we refer to as trough. Then the next one is amplitude. Amplitude simply means the maximum displacement of a wave from its equilibrium position or from undisturbed position. When you talk about the undisturbed position, we are talking about here. This is an undisturbed position, or you call it the equilibrium position. So the maximum displacement from this point is what we refer to as amplitude. It can either be upward or downward. So from here to this point is called amplitude. Likewise, from here to this point is also amplitude. Maximum displacement away from the undisturbed position. Okay, the next one is wavelength. When you think about wavelength, it is the distance between adjacent trough to the other adjacent trough. The distance between two troughs is called wavelength. And it is denoted with the Greek letter lambda. The Greek letter lambda is used to denote wavelength. It can either be the distance between one trough and the other, or the distance between one crest and the other. So when they say the distance between two adjacent crests is known as wavelength. And is denoted with lambda. You can also say wavelength is the distance from this position to this position. Are we together now? The distance from this position to this position is also what? Wavelength. So we just have to understand that it is measured in meter. Likewise, the amplitude is also measured in meter. Good. The next one is frequency. Frequency is the number of cycles per second. That is The number of cycles that you complete in 1 second is what we call frequency. For instance, if this body moves from here to this place, this is 1 cycle. If it moves from here now to this place, this is another cycle. So this wave profile now consists of 2 cycles. But if the time that takes this body to complete the first cycle is not up to 1 second, are you getting this now? It means what? The frequency cannot just be 1 cycle. We'll get to that as we move on. I will explain that better. But when you say the number of cycles that a body completes in 1 second is what we refer to as frequency. It is measured as per second. Cycle per second, or you measured it as hertz. Are we together now? That is the unit of frequency, and it is denoted by letter F. Good. The next one is period. When you talk about period is the time taken to complete 1 cycle. The time that takes you to complete 1 cycle is what we refer to as period. So, if from here to this place is half cycle, then from here to this place is another half cycle. Half cycle plus half cycle will give you 1 cycle. The time that takes this body, this particle, to move from here down to this place is called the period. It is denoted with capital T and it is measured in seconds. Do we understand this now? Now, it's possible that they ask us to determine the value of amplitude, to determine the value of frequency, to determine the value of wavelength, to determine the value of period. How do we go about that? Let's quickly look into that. Okay, good. Let's consider this wave profile in order for us to calculate the value of amplitude. Let's say this is the maximum displacement and the value is 8. And here is the displacement downward and the value is -8. Are we together? Displacement from here to this place is 8 and from here to this place is -8. Now the question now says you should calculate for amplitude. How do you calculate for amplitude? Amplitude equal the value, the higher value, that is the crest. Let me put it like that. Crest minus trough divided by 2. Your amplitude is given as crest minus trough divided by 2. That is, our crest is 8. So I have 8 minus our trough, -8, divided by 2. So we have that amplitude equal 8 plus 8 divided by 2, and that is 16 divided by 2. So our result is going to be 8 meters. So the amplitude of this wave is 8 meters. Do you understand that now? So whenever you are looking for the value of amplitude, it's just crest minus trough. Now, there are some cases whereby you are going to be given a wave profile that is not balanced like this. How do you do about that? Let's see. If I'm given a wave profile like this, at this now, this undisturbed position is not exactly half of this circle. Are we together now? Let's say this displacement upward is 8. Are we together? If the displacement upward is 8 and the displacement downward like this from here to this place is -4. Are we there? Here is 8 and here is -4. Before we can determine the value for the so-called amplitude, we have to look for the amplitude of the wave. If you take the amplitude to be from here to this place, it will be wrong. Are we together now? So the first thing to do is to find the midpoint of this wave. When you find the midpoint of this wave, then we can now determine the value for the amplitude. Although, if we apply the exact equation that we are using, we are still going to arrive at the same answer. Is that taken up? So now let's quickly look into that. For me to get the center mark of this now, what I will do is that I will have 8 plus minus 4 divided by 2 for me to get the midpoint of the wave. This will then give me what? 4 divided by 2, and this is going to be 2 meter. So that is 2 meter. Therefore, the midpoint of this wave, is going to be 2 meter. Do we understand this now? So, if the midpoint is 2 meter, I can now determine my amplitude. My amplitude is going to be 8 minus 2. Are we there now? 8 minus 2. That will give me my amplitude, and that will just be 6 meter. And if I want to use the said equation, that is the crest minus the trough, then I will have that A equal 8 minus 4 divided by 2. So A becomes 8 plus 4 divided by 2, and that will be 12 divided by 2. So that gives me 6 meters. So you can decide to use any of the two. Do we get that now? And that is how to determine the value of your amplitude. Now, how can you determine the value of your frequency? The value of your frequency and that of the period. We need to understand that when you are talking of frequency, frequency is given as the number of cycles divided by the time that takes to complete that number of cycles. And period is given as the time taken to complete number of certain cycles divided by the number of cycles. Are we there? This one is measured in second, and this one is measured in hertz or per second. Do we understand this now? Good. If that should be the case, I can say that frequency is 1 over period, or I say period is 1 over frequency. So if that should be the case, you can see the relationship that exists between frequency and period now. Now let's take for instance that we are now given a wave profile, and we are asked to determine the value of frequency or the value of period. How do we go down? Let's see. Let's say I have this. This is half circle, half circle, half circle, half circle. If from here to this place is 0.2, are we there? Okay, let me say from here to this place is 0.1, 0.2, 0.3. This is time in second, and this is displacement in meter. Are we there? Now, we are asked to find the value of frequency of this particular motion. That is, if you are given this wave profile, you are asked to look for frequency. They want to know the number of cycles that we are going to have on this wave profile in 1 second. That is the aim of the examiner. Find the number of cycles per second on this. Now let's see. How can we go about that? Since here is the time that takes us to complete 1 cycle is what we refer to as period, right? Now this is half cycle, and this is a complete cycle here. Therefore, T equal 0.2 second. Now, frequency is 1 over period, isn't it? Therefore, we have that 1 divided by 0.2 is going to be our frequency. And 1 divided by 0.2 will give us 5 hertz. So that means that if I keep on drawing this circle, let's see what we are going to have. Our frequency is 5 hertz, isn't it? It means for 1 second, the circle that we are going to have on this profile is going to be 5 complete circles. Let's draw that and see if that will be true. So I have, okay, this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, then 1.0. Okay, I think I can clean this. So this is time in seconds. You can see that we've gotten to 1 second there, isn't it? Now let's count. This is half circle. This is 1, 2, 3, 4, 5. You can see, and you see our frequency is what? 5 Hertz. Do you understand this now? So this is how to determine period and what? Frequency. If I give you that the frequency of a system is 5 Hertz, calculate its period. So that means that I will just say T is 1 over F, that is 1 divided by 5, and this will just give us 0.2. It shows that it will take 0.2 seconds to complete 1 circle. If you complete a circle, are you getting it now? If the number of circles that you complete in 1 second is 5 Hertz, it shows that it's taking 0.2 seconds to complete 1 circle. Do you understand this now? Good. Okay. So now let's look at the other formula, that is that of the circle. If I say that a body completes 20 oscillation in 5 seconds, a body completes 20 oscillation in 5 seconds, calculate the period of the motion. So period is going to be the time divided by the number of circle. Therefore, I will have 5 divided by 20. Do we get this now? And this will just give us 0.25 seconds. That's the period. That shows that if a body completes 20 cycles, are you getting this now? In 5 seconds, it means it's taking 0.25 seconds to complete 1 cycle. Do you understand this now? So what did they now say? What is the frequency? The frequency will then become the time, the number of cycles divided by the time. So the number of cycles is just what? 20, and the time is what? 5 seconds. That means this is 4 Hertz. That shows that this particular body is completing 4 cycles in 1 second. Do you understand that now? That is that about frequency and period. Do we get that now? Now, wavelengths. For us to get what we call wavelengths, there is need for us to create, we can start by looking at the velocity of the wave, because when you talk about the displacement of the wave, if you want to talk about where the wave is going to be in the next moment, you have to know the speed of the wave. Are we together now? So we have that velocity is given to be distance, that is displacement, divided by time. Are we there now? Now the displacement divided by time is what will give us velocity. Are we together? Okay, if this should be the case, velocity is equal to distance over time. Our distance is the same thing as saying what? Lambda. Because the distance between one adjacent crest to the other is lambda. So V now is equal to lambda divided by what? T. Do you understand this now? Velocity is equal to lambda over T. Therefore, wavelength is velocity times the period. Now, if you recall that period is 1 over frequency, then you'll be having that lambda is equal to velocity over frequency. In other words, velocity equal lambda frequency. Do we understand this now? So with this, we have created relationship between lambda and period, and we also create a relationship between lambda and frequency. Do we understand this now? Good. Now let's quickly look at the properties of wave now. Properties of wave. When we talk about the properties of wave, we have 1, reflection. We have 2, refraction. We have 3, diffraction. We have 4, interference. We have 5, polarization. Now let's quickly explain all this property about wave. These are the property that a wave can exhibit, but for this particular last one, is not what all wave that can exhibit this property. Are we there now? Only some wave, which we are going to discuss as we move on. Now, reflection. What is reflection? When a wave travels and encounters an obstacle, that is, the wave can no longer go in that direction again, and that is because as a result of that obstacle, it changes its what? Direction. That is what we refer to as reflection. For instance, that is, let me take 12. Reflection is the change in direction of a wave when it encounters an obstacle. If I have a surface like this, and I have a light ray coming straight like this, because of this surface, this light ray is said to reflect to the other direction. This particular ray is called the incident. The incident ray. And this one is called the reflected ray. Are we there now? This is the ray that encountered an obstacle. It will be called incident. The direction in which it changed to, that ray is going to be a reflected ray. You can see that this wave changes direction because of this obstacle. Do we understand that now? Thus, this is a reflected ray. Now, if I draw a normal, ON, let me call this N and call this O. The angle between the normal and the incident ray is called the angle of incidence. And the angle between the normal and the reflected ray is called the angle of reflection. But angle of reflection is equal to angle of incidence. Do you understand this now? I will be equal to R. We'll talk about that as we move on with this topic. Do you understand that now? The next one is refraction. Refraction is the property of a wave that is characterized by changing medium. When a wave moves from one medium to another, what will happen is that the speed of that wave would change. Wavelength of the wave will change. The direction of the wave will change because it moved from one medium to another. For instance, if you hold light, like a torchlight, if you put it on air and you just what? Touch it inside a water. If the light should pass from air into water, what will happen? The speed of the light will change. The direction will change. The wavelength will change. The only thing that will remain constant, that is unchanged, is the frequency. Are we together now? So when a wave changes its property as a result of moving from one medium to another, is what we refer to as refraction. In other words, we can say the change in direction of a wave as a result of moving from one medium to another. Now, how can we then get the value for the speed of a light, for instance? Let's take light for instance, in different medium. Let's take for instance that light is traveling from air to water. And we said once it's traveled from air to water, the speed will change. What will be the speed of light inside water? Now, we have this formula that the speed of light in any medium is equal to the speed of light in air divided by the refractive index of that medium. Are we making sense? The speed of light in air or vacuum is 3 times 10 raised to power 8 meter per second. And that is the reason why you cannot say the speed of light is constant. No, the speed of light is not constant because it has different values in different medium. Now, the refractive index of water is 1.33. That is the refractive index of water. Therefore, the speed of light in water will become 3 multiplied by 10 raised to power 8 divided by 1.33. So, what are we going to get for that? So, if I have 3 times 10 raised to power of 8 divided by 1.33. So my result is going to be 2.25 times 10 raised to power 8. 2.25 times 10 raised to power 8 meter per second. You can see the speed has changed. It's no longer what? 3 times 10 raised to power 8 again. Why? Because it's moved from one medium to another. Now, what will happen if the refractive index is 1.5? Instead of 1.3 now, that is if the light move from water, if the light move from air to glass, the refractive index of glass range around 1.5. Are we there? If the refractive index of the glass prism is 1.5, what will be the speed of light in it? So we have that V equal 3 times 10 raised to power 8 divided by 1.5. So we therefore have that this will give us 2 times 10 raised to power 8 meter per second. You can see now that the speed of light in water is greater than the speed of light in glass. This is the speed of light in glass, and this is the speed of light in water. Why is the speed of light greater in water than that of glass? Because the refractive index of glass is greater than the refractive index of water. So the higher the refractive index of that medium, the lower the speed of light. And don't forget, the only thing that will remain constant about the light that change from one medium to another is its frequency. Every other thing about the wave is said to do what? Change. But the frequency will remain unchanged. Do we understand that now? Good. The next property is diffraction. Diffraction is the spreading out of a wave when it passes through an opening. When a wave passes through an opening, the spread out of it is what we refer to as diffraction. We define it as when a wave bends round its obstacle. When a wave bends round its obstacle, we call it diffraction. For instance, if I have something like this, let's say I have a screen. This is a screen, and this screen has an opening. Then here we have light waves that are traveling on a straight lines like this. Now this is an obstacle that will cause them to reflect just like we have this. But because of this opening, once they are able to pass through here, they are said to spread out. The spreading out of a wave, or what we refer to as bending around its obstacle, is what we refer to as diffraction. Then this diffraction now depends on wavelength. That is the opening of this aperture. That is the wavelength of this aperture is what we refer to as the factor that determines the rate of diffraction. Are we together now? If the wavelength is small, the diffraction will be great. If the wavelength is high, the diffraction will be small. That is, diffraction is inversely proportional to the wavelength. Are we together now? So if I have a very wide opening, you see the wave moving straight like this, instead of bending around the obstacle at this great manner because of the small opening. So diffraction is depending on wavelength. While refraction is depending on refractive index of that particular medium. Do we understand that now? Interference. When you talk about interference, interference occurs between two waves that are combined together. Combination of two waves is what forms what we call interference. And it can either be constructive or destructive. It's said to be constructive if the two waves come together to form what? Another bigger wave. It's going to be constructive, or you call it reinforcement. But when the two waves come together and do what? And cancelled what we call the wave at the point at which it comes together, that is called destructive interference, or you call it cancellation. Let's see what I'm saying. If I have a wave profile like this for two waves, like this, they both move with the same amplitude, like this. Sorry. Are we there? Now, these two waves, they come together here. They come together here, and they do what? They form a bigger wave. Are we together? These two waves, they combine together to form a bigger wave here. Here we have a constructive interference. Constructive. Because the coming together of these two waves results to a bigger wave. But when you look at this point here, the two waves come together and there is nothing like wave on this place. Here they have what we call destructive interference. Are we together now? Or what we refer to as cancellation. Do we get this now? Good. Then the next one is polarization. Polarization is the confinement of a wave to one direction only. When you confine a wave to move in one direction, it is called polarization. Do we get this now? We refer it to polarization. So, polarization is only peculiar to transverse wave. That is, a wave that can be polarized is a wave that travels perpendicular to the source that is producing it. We are going to look at that now. Let's look at type of wave. The types of wave. Okay, types of wave. So when you talk about the types of wave that we have, guys, we have one, longitudinal. We have transverse. We have standing wave. We have progressive wave. Progressive wave. Now let's discuss these types of wave here. When you talk about longitudinal wave, a wave that travels in the same direction as the source that is producing it. Like this. So the source that is producing this wave, that is the direction of the wave, is the same thing as the direction of its vibration. When the direction of the wave is the same as the direction of its vibration, you call such wave a longitudinal wave. Example of longitudinal wave includes sound wave. Are we there? Then transverse wave. A wave that travels perpendicular. A wave that travels perpendicular, this is the direction of travel, and this is what? The vibration. So you can see that the traveling direction and the vibration are perpendicular. Such wave is referred to as transverse wave. Example of such wave includes water wave, and all EM wave. That is all electromagnetic wave. Any wave that is electromagnetic wave, either radio wave, infrared, visible light, light wave, and so on like that, they are example of transverse wave. The only mechanical wave that is transverse wave is water wave. Do you understand that now? Good. The next one is standing wave. Standing wave can occur between longitudinal or transverse. It occurs between two waves that has the same frequency. The two waves has what? The same frequency, the same period, the same amplitude. Everything about the two waves is the same, but they are opposites in direction. When two equal waves move in an opposite direction, the kind of wave they are going to produce is standing, or you call it a stationary wave. That can happen within any type of wave, either longitudinal or transverse. We are going to talk more about this particular concept of wave. That is, the standing wave is a topic that we are going to look on its own, where we are going to be discussing the node and the antinode. Are we together now? So let's go on to the next one, progressive wave. A progressive wave is a wave that travels continuously. A wave that travels continuously is what we call progressive wave, or you call it what? A transverse wave. So any wave can be a transverse or any wave can be a progressive or a traveling wave. Just like any wave can be stationary wave. Are you getting it now? Or you call it a standing wave. That's that about that. So before we call it a day on this topic, let's quickly look at the equation of a wave. Now, if I have equation of a wave, equation of wave, or wave equation. Anyone? You right? So guys, let's see. If I have a wave like this, this is a sinusoidal wave that has an angle theta from its displacement. This is called angular displacement. Are we together now? And it has a phase difference phi. Now let's quickly show the relationship to represent all these characteristics on a wave. This is lambda, and here is the displacement in the vertical direction. Are we there? Here can either be a function of position or a function of time. Now, I would like you to consider this circle. For a body that is oscillating, if here is the radius of the circle, this is going to be the amplitude, and here is going to be theta, which is the angular displacement. Are we there? Now, if this is the displacement y in the vertical direction, if I say sine of theta is said to be opposite over hypotenuse. So if I cross multiply here, I will have that y equal a sine theta. If y equal a sine theta, if I consider the phase difference of all these particles on this, I will have that y equal a sine into theta plus or minus the phase difference. Now, this is plus or minus the phase difference. I will explain when it's said to be plus and when it's said to be minus. Are we together now? Now, let's move on and see. The phase difference is given as 2 pi x all over lambda. Are we together now? The phase difference is given as 2 pi x over lambda. Why? Because k, which is a constant here, is given as 2 pi lambda. I'm showing you this because some textbook we say phi, which is the phase difference, is equal to kx, where k is a constant which is 2 pi over lambda. That is, if I will talk about what? Lambda, I must have been talking about what? A complete circle. One wavelength is one complete circle. Are we together now? So if I will get a wavelength now, from here to this place is one wavelength. And you can see that it has complete one circle. I would like you to pay attention here. from here to this place is one circle. Are we there? Which is 2 pi. And this is what? One wavelength. So 2 pi per wavelength. That is one circle per wavelength is a constant for this wave. Do you understand that now? For any wave, one circle per wavelength. Now, the position that one circle might be, it's also needed to be what? Considered. Because if this is here now, this is one circle, and it's also here, this is what? 2 circle now. That is, the value of x must become what? 2. In order to show that we are having 2 circles. I would not like to talk much about here in order not to bring confusion. So let's go back to where we are. So we then have that y is equal to a sine into bracket theta plus or minus what? K plus or minus 2 pi x over lambda. So here is the general equation of a wave. Now this theta, I can define theta as omega t, because angular displacement is what? It is angular, when you say angular velocity rather, angular velocity is equals to angular displacement per second. That is, omega is theta over time. If I cross multiply, theta will become omega t. Therefore, y equal a, which is the amplitude, sine omega t plus or minus 2 pi x over lambda. Are we there? Now, if omega is equal to 2 pi f, then I can say y equal a sine 2 pi into bracket ft plus or minus x over lambda. You can generate as much equation as you want from here. Are we there now? So this is the general form. Now, when it is positive, it shows that this body is moving towards the negative axis when it is positive. But when it is negative, it shows that it's moving towards the positive axis. At this junction, I would like to stop here. Then, in our next class, we are going to continue from there, where we solve more questions on this and explain every other thing as regards wave. Then we'll consider the standing wave in that class. Do have a nice day. If you are yet to subscribe to this channel, kindly do now. Love you guys.